Okay, so good morning. My name is Roberto Gonzalez, and this is the Purdue project Clinker part. So the first question asks us is to select any reaction that is likely not happening inside the kiln and eliminate from the table. So the main difference, the project states that it's white kiln that it's being used, not regular kiln. So the basic difference is that regular kiln has iron involved in its equations, in its reactions. White kiln does not. Therefore, we just need to eliminate any reactions that have, iron. And in this case, it will be reaction B and reaction E. The second question will be to calculate the enthalpy of formation at 298 Kelvin for each of the remaining reactions. So we're going to use the first reaction as an example in this case. So we just need to check each individual mineral compound formula. So for example, for a whole, so the reaction itself, the answer is 1. Then SiO2 is another one, and it's 2 SiO2, so we multiply that value by 2. These values are given to us in a table that was in the problem. So we just do that, multiply by 2 when necessary, and it will give us this delta H HF 298K in kilojoule over mole. So when we have those values, we just do a sum. This one's in the 4120.4, since it's on the left side, we just pass it positive to the right side and it stays positive. And then we just subtract the rest of it, and it will give us this answer, 139.9 kilojoule over mole. Now we just need to repeat this process for each reaction, and we get these values: 139.9, 230.2, 527.3, 178.3, and 13.4. Next question, calculate the total enthalpy change for each reaction, assuming that the reaction occurs at the temperature given in the third column of the table, delta H 288K plus sensible heat. So we have this base formula, which is delta H, the total, equals the delta H 298K, which we got in the previous problem, and then we integrate our next temperature, the temperature of the specific value of the specific reaction, over 298K, which is our temperature, and we just add the sensible heat, A plus Vt plus Ct minus 2, O2 minus 2, and dt. Heat capacity, as I mentioned earlier, is given at the table, but it's in joules over mole times Kelvin. So we must convert it to kilojoule mole times Kelvin. So we just move the point three steps to the left. Using another reaction, 2CaCO3 SiO2 to C2S plus 2CO2, as an example, we get this table. This is the compound of each individual part of the formula, the reaction, and this is its specific value already converted to kilojoule. So it's the value, you just move the 0 3 spaces, and this is what we get. We then add each individual A, Bt, and Ct all together, so we get these full values. And these values are the ones we substitute in the formula. Now the temperature for this specific reaction is 1048K, so that's the temperature we're going to be using in the top spot for our T2, and this is the delta H specific for this reaction. And once we get that, this will be our reaction, our delta H total in kilojoule mole, 274.3, and we again repeat for each reaction, and we get these answers. This is the respective temperature for each reaction, and this is the total already, delta H in kilojoule. So now the next question is to transform the total enthalpy change to kilojoule per kilogram of clinker using the conversion factor given in the fifth column of the table. This is pretty easy. We just simply multiply our delta H total from the previous problem and multiply it by its corresponding conversion factor. Using the same reaction as before, as an example, this is a reaction. This is the H total that we got in the previous problem. This is its conversion factor, And this is our answer for this question, 982.9 kilojoule over kilogram clinker. So it's just a simple multiplication. And again, repeat for all reactions, and we should get these answers. This is our H total. This is the correct answer. The H total kilojoule over kilogram CLK. Number 5 is to determine the total enthalpy change for all the reactions. Overall energy requirement in kilojoule kilogram clinker to complete the clinkerization progress. We just add all the previous problem's answers. So all of this, 55.16, 98.2, 982.9, and so on. And we get a grand total of 1,836.1 kilojoule over kilogram clinker. Question number 6, what is the calorific value for a fuel? Make a quick research, blah, blah, blah. A fuel's calorific value is the amount of heat released by a unit weight or unit volume of the fuel during a complete combustion reaction. If question number 7, if petroleum coke is used in this clinkerization process, how many metric tons of this fuel are required per hour to complete the process? So before we get into the math, we must know that the calorific value of petroleum coke, it can be calculated by processing temperatures and its constant pressure molar heat capacities. This value allows engineers to know how many metric tons of petroleum coke are required per hour to drive this clinkerization process. So once we get this quick formula, we got the 30 tons of raw meal as stated in the problem, 1,000 kilograms. We just do basic arithmetic. We basically just need to isolate M coke. These values are given to us in the formula or by the teacher, and as a professor, I'm sorry. And we get a grand total of 1.18 tons per hour of mass of coke. Therefore, 1.18 tons of petroleum coke are required per hour for 30 tons per hour of raw meal used. Next question. If reaction G, the last one from the table, occurs at 1,633 K, and assuming the clinkerization process stops at that temperature, what is the final phase expected for C2S or B light? Assume there is only CaO and SiO2 in the system. Okay, so first for our phase diagram, which we have here, we need to convert this 1,633 K into Celsius. Therefore, we just subtract 273 and we get 1,360 Celsius. Knowing this, we're also assuming that there's more than 20% of SiO2, so as instructed by the professor. We conclude by looking at the phase diagram that the final phase will be C3S plus alpha minus C2S. Now, in order to prove that, our 1360 C should be around here, is the half, so yeah, around here should be good enough, a little bit more on top. And since it's more than 20%, we could assume that it's just around this as well. And once the two arrows converge, we get precisely C3S plus alpha minus C2S. That's this little square right here. That's simple. Question number 9. On the ternary phase diagram on the next page, shade the region of the SiO2 minus La2O3 system that corresponds to white clinker. Okay, so we need to use this table, also given to us in the problem, and we're using clinker 24. This is the one we're using. So now we just need to use these values in order to use it in our ternary diagram. So the way to read this diagram is SiO2 values start here at the top, at the tip of the triangle, and go downwards all the way to 100. So in here we have 0, then we got 10, 20, 30, and so on, all the way to 100. From La2O3 is the opposite. We go from 0 on the bottom, from 100 in the bottom to 0 on the top, but we read backwards. So this is 90, 80, 70, and so on. And from CaO, I'm sorry, we read from the left bottom side to the top side. So it's 10, 20, 30, the way it's here. So The value for SiO2 it's 21.64, for CaO it's 66.71, and for Al2O3 we get 5.52. Now we have the colored so we can identify the lines. So for SiO2 we go to 20 and we just, since it's 90, 80 and so on, here's 20 and we just write across. For CaO2 it's 66.51, and oh, I forgot, it's not this way, it's this way, from left side to right side. So we just grab our 66.51, so it should be around here. Minor mistake on my part, I'm sorry. And we just across all the way. Next, for Al2O3, it's 5.52, so since we start from here, this is 0, so this is 5 approximately. So we just draw a line all the way across. And we're going to have a crossed region, a triangle. And this black area is our shaded area. So this is the region, the CaO minus SiO2 minus Al2O3 system, it corresponds here to white clinker. And the last question, to mention at least 2 reasons that could force engineers in a cement plant to take the decision of increasing or decreasing the TPH of petroleum coke required for this kiln. So many options are included, many options are available. So the main ones I would think about is to lower petroleum coke. This will reduce CO2 emissions, which is also good for the planet. It will also, a decrease of petroleum coke can reduce sulfur, which again is beneficial for us. And well, not only that, but we need to do that because you cannot have sulfur. Therefore, it will be a way to force engineers to make this decision of decreased petroleum coke. Then, and our last option, well, in here, would be if a significant amount of heat is lost to its surroundings, an engineer will want to increase the tons per hour of petroleum coke used to compensate for the loss of energy. It will also be something to not decrease, but to increase. So the question doesn't specifically ask to decrease, and I mean one of both. It asks what would both happen. So these 2 would be to decrease the TPH of petroleum coke, and this one would be to increase the TPH of petroleum coke. So both options are available. And that would be the end of this presentation. Thank you so much for your time, and have a great day.